The topic that I will deliver in this inviting talk is the innovation in high performance knowledge graph processing. It is indeed an honor to be here at the International Conference of Computing and Innovation. My name is Dr. Usman, and I am working as an assistant professor in Arden University, Berlin. And thank you, Dr. Shahryar, especially for inviting me to share the idea. So today I will be sharing my work on the link open data. Uh, First, I will explain what will be the content in this short presentation. I will try to finish this presentation in 20 minutes. Before I begin, I would like to give you what will be the agenda or what will be the content in this presentation. So this work, I will first start with this by giving you an idea what this link open data means and why it is important. So I will start with the motivation. I will start with the research taxonomy. The idea is to give you the high level picture why I must say it is important in building up some data driven application. Then I will summarize the relevant work which obviously I have collected from the different journal and also try to compare my work with the existing one. The main thing that I will emphasize is about this methodology, so which I have proposed especially to overcome the challenges in curing the link open data cloud. In the experimentation part, I will also give you the result that I have collected after implementing it, and then we will continue to the future work how we can utilize it. So let's begin with the background. Link open data, which normally sometimes we call as a LOD, is a kind of a distributed knowledge base. And it why it is important nowadays because it's publicly available. The data is free of cost, but the data has some format. Uh, and it is an interconnected kind of a web of data set. Let's suppose if there is a data set of healthcare and it is connected to some biotechnology and biotechnology is connected to chemistry. So all these data set or some other government data set that all are connect together, and that is we call as a linked. And this data also present in a specific format we call as an RDF. Like and this and there is a way to query that RDF. We normally use this Sparkle language, which help you to query the data. Now, the problem is because of this huge amount of data and this data is continuously growing. So there is a problem to query it. So we cannot find a suitable approach to query that data. So in traditional ways, there are two ways to query this data. Let's suppose if I want to build up an application that is using this link open data. So one approach I can use is I just download the data set from the public link open data cloud and then maintain the local copy on my hard disk. So what will be the benefit? It will be easy. Obviously, I just need to download it and then I need to just configure and then put my application on the top and then available for the queuing. Um, but the bigger problem is that my data set will be outdated quickly and I need to re-download it again and again. So it's not an optimal solution. And also I need some infrastructure to keep it up to date. The second idea is uh, instead of downloading to the local, you just utilize. Why don't you utilize the endpoints? Like you use some APIs, you can connect that API to those publicly available endpoints. So that is also the second approach. Uh, but sometime if let's suppose you have put your application with the help of this API and somehow this API is not working well and that often the case of link open data. The APIs are not publicly available 24/7. There are some downtime happen, low availability, which I mentioned in my research. So all these things are very frustrating for the data scientists to apply it. So here is the solution which I have proposed. So I have proposed a cache-based solution because I will go with the second idea of querying the endpoint, but still uh, how you can optimize it. So this is the way we call as a client-side caching approach. So this caching will help us to better understand what content should be cached and how to optimize the query. I will go into the detail when we go into the methodology section, but this is the overall motivation that I want to start with. Uh, and then by this motivation, we can quickly go through the what is the research taxonomy will look like. So this is basically a problem of information kind of a retrieval or information search. And instead of relying on server-side caching, I propose the idea of the client-side caching. And this is how this idea will goes further into to the similarity matrix because I want to capture the data that are changed. So I have proposed this approach of change matrix. And to optimize the query, I propose this query augmentation, and also to optimize the cache. Instead of time-based replacement, I propose something called frequency-based replacement. So this is the formalization of the research problem. The research problem itself is highlighted over here. You can read it. I think it is self-explanatory. I have put the references over here which help you to understand this is a common problem, and other researchers are also trying to work on this problem. The bigger goal for our case is to improve the bottleneck and also improve the query time of the link open data. Obviously, we have established some objectives. We need to design something called client-side caching. We also need to, and then we need to decide some trade-off between the data availability and query performance. To overcome these objectives, there are some challenges that we need to consider because it's a link open data and it's also evolving. So due to this evolution of this data that make things more difficult, and the first thing is about our cache obviously get uh, get outdated very quickly. The second problem is that how you can find the similar patterns or similar data because it's a linked, and sometimes we are not sure which data we should query. And also the problem with the cache approach is that the cache itself is very limited in size. So how you can make it more valuable so that you can replace more often. So that is basically our whole idea of this research problem. So in this slide, I have summarized some of the work which are considered as very similar, but still they are mostly relying on the server side caching. They want to make optimize the server, but but my research argue that instead of optimizing the server, still server have some limitations. So you can put the caching on a client side, and then it will help you to obviously help you to query the data. It will eliminate a lot of different problems. So this is the relevant work. And the bigger thing that I highlighted is the overhead. So if it also reduce the overhead when querying on the data. So let's visualize how this works. This is the bigger picture of the idea. So traditional system relying heavily on a server, leading a bottleneck, and our approach shift the intelligence to the cloud. So this is the main idea behind it. So client maintain local caches that are dynamically updated based on the link open data evolution. And then the similar queries are executed once and results are stored to the future cache. And then we also propose in a solution to about some kind of the cache replacement, is we call as a smart way to replace the cache. This will not only reduce the server load but also improve the query performance for the end user. This is the bigger picture of our approach. Uh, and then I will highlight it. What are the three key innovations? So the first innovation is the use of the dynamic function, because this is the linked open data and everything is evolving. So the better way is you don't need to capture all the data. You just need to capture what is already updated. So we need to use some type of a function that will only quantify what is already updated. And the second thing is about the query augmentation for prefetching. So by analyzing the query pattern, we can prefetch the result from the similar query before they are ever issued. That is also an idea which and what benefit it will bring. So this reduce the server load and speed up the response. And the third one is which is about the cache replacement. So we also propose another algorithm. Instead of relying on the time, we use the frequency. So most, like, the idea is the most frequent queries will be placed in a cache. That is our basically solution. So these are the key innovations. I can go into the each solution for you have more understanding if you want to reuse these some of these solutions, because all these solutions are already published in a journals. If you want to reuse it, then you can get an idea after I will explain like this. So this is the solution one, which is about the use of um, the dynamic function. So we develop a dynamic function to quantify the evolution of link open data. This helps us to understand how link open data change over the time, because we want to capture this evolving nature of this data. And also we want to prioritize the update to keep the local cache fresh. And second, we have implemented something called query augmentation, which I will obviously explain. So this is the main idea of the change matrix. So which function that change matrix will use? It's use a dynamic function. We use the Jaccard similarity index to capture what is basically if something is more item have been added, removed. So this Jaccard will give us some type of a measure that which item has already updated. So which item you need to capture. So our solution is a dynamic function denoted as this figure that quantify the change in a real time. So this function measures the addition, modification, and deletion of a triples. For example, if a data set like dbpedia is updated frequently, so our function will detect that these changes are prioritized, updating the local cache for that data set. And this also ensure that the user always have to access the most current data. So unlike the existing approaches, they're relying on a static dump or page rank or dynamic function, uh, and this dynamic function is more flexible or adaptable, making it ideal for like evolving nature of a data. And the second solution that we have proposed in this research is to how we can implement. So we have proposed two more algorithm, and they are also internally they are using this dynamic function, which obviously use a change matrix. So application aware change prioritization. This is the first algorithm that I have proposed over here, which is abbreviated as AACP, like application aware change prioritization. So how this algorithm will work? This algorithm assign a weight to the change in the link open data cloud uh, based on what is the recent change and what is the relevant change. For instance, if a data is updated frequently, then this algorithm will prioritize this change over older and less relevant updated. So the goal of this algorithm is to ensure that the most important and recent changes are reflected in the local caches. The second algorithm which we have propose is this preference aware source update algorithm. So here we have used something called uh, you need to, the main idea is to we need to the maintenance policy only visit the sources that have been changed in the recent past. So it should not be that you should maintain or you should maintain all the copy. You just only need to define a preference, like either you should copy the most recent changes or not. So this is the next we will talk about the query augmentation for the prefetching. So one of the biggest challenge in querying the link open data is the repetition of the similar queries. For example, if a user uh, uh, might issue a slightly different query that retrieves similar data, then obviously it will increase the server load. So our solution is to analyze the query log and identifying the patterns when a user issue a query, or our system prefetches the result from those query that are likely to be issued in the future. So this algorithm will try to analyze the log, and then they will prefetch it so that there will be a less burden on the server side. So this approach is useful in a scenario where the user issues repeated or predictable kind of a queries, such as research or data analysis application. You can apply this type of approach. And to implement the query augmentation, we use the two technique we call as the query suggestion and query relaxation. This is also kind of innovative because it is not used in the state of the art approaches. So this technique analyze the past queries to identify what patterns and also suggest the similar queries that might be issued in the future. For example, if a user frequently query for the information about the universities, so our system will suggest the prefetching result of the relevant queries about the academic program, about the research publications. So query suggestion is based on both structure and the content of past queries to ensure that the prefetch results are relevant and useful. And the second approach that we have proposed is the query relaxation, which goes to the a step further by modifying the queries to retrieve the additional information that might be useful. For example, if a user query a specific entity, or a system might relax to query the relevant entries or broader the categories. So this technique also ensure that the cache is filled with the valuable data that can be answer a wide range of queries. Uh, and this can also bring lot of benefit for the data driven application. So together with the query suggestion and query relaxation, which making our prefetching system both intelligent and adaptive, and ensuring the user have a fast access to data that is required. This is also the query relaxation. We apply something called query template. So based on the template, we just prefetch the queries. This is the internal detail of how this query prefetching work. Maybe I will skip this algorithm. I will give you the brief idea already that how prefetching is important in the perspective of data intensive application where client required to query the data again and again. And now, after explaining the solution one, and we move to the solution two, which is about the cache replacement. So let's discuss the frequency-based cache replacement policies, because in the existing work they mostly consider the time base. So based on the time, the cache will be updated. So our idea is to more about the frequency. So traditional cache replacement policy like LRU or LFU, LRU mean the least recently used or least frequently used, that often replace data based on a time. So however, these methods don't always reflect the true value of a data in a cache. So our approach is different. instead of replacing data based on a time, we track how often the piece of the data is accessed because we already propose an algorithm. So data that is accessed frequently is considered more valuable in our case and retained in a cache, while less frequently accessed data should be replaced. For example, if a data set about the popular research topic is accessed often, so it will stay in a cache. And even if it is older, on the other hand, if the less popular data set might be replaced to make more room for the valuable data set. So this policy ensure that the cache is filled with the most relevant and useful data, and also maximize the hit rate and minimize the overhead. This is one of the how this frequency based algorithm work. So we use this exponential smoothing kind of a forecasting variable that we have used mostly, and this is borrowed from the other techniques of statistics where the exponential smoothing is mostly used for the forecasting the data or forecasting the stock. But we get the idea from this smoothing function and apply it into the cache replacement part. Let's now move to the experimental section. So in the experimentation, we put our methodology to a test. Uh, and then we also compare it with the candidate approaches. We also mentioned that the valuation metrics that we have used. So overall, the data set that we have utilized is these two data set because this data set is available for the every month, and we can able to capture the evolution of these data set. uh, and and also we have compare these two data. These are the characteristics, but is inside the data set that is present. Our evaluation metrics is accuracy. We use effectivity and also performance. Let's dive into the results, starting with the maintenance quality. So our goal here was to evaluate how well the maintenance policy keep the cache up to date. So we measure the F measure score. We combine precision and recall to provide a single score of accuracy. Our proposed approach achieved the F measure of 90% as compared to the other state-of-the-art approach like page rank and age-based replacement, which score obviously poorly because they either focus on irrelevant metrics or fail to adopt the dynamic change in the data. So in contrast to the dynamic function and algorithm that we have proposed, that the cache are always up to date with the most relevant and the recent data. And this high F measure also demonstrate the effectiveness of our approach in maintaining the cache accuracy and even in the link open data cloud. Uh, we also take into the maintenance quality. So this table also compare into the different data set. The total query execution in our approach is 19,000. If you can compare, if you in this table, I have just summarized the irrelevant. You see the most of our approach, they execute less irrelevant queries as compared to the other approaches. So this result highlight the efficiency of our approach by focusing only on the relevant updates and minimizing the overhead. We can claim that we can create an accurate and fast retrieval of the data. Um, Now let's discuss about the maintenance cost, which refer to the time and the resources required to keep this cache up to date. So our approach significantly reduced the maintenance time compared to the existing approach. Strategies like page rank, size, uh, also are all are all are basically containing some poor performance in this diagram. So in contrast to our system performance, we reducing the impact of the performance. Uh, and as a result of our approach, we achieve a lower time of just 5 seconds as compared to the much higher time for the existing approach. So by reducing the maintenance time, what will be the impact? So we improve both the performance and the scalability of a system. So make it ideal for a data intensive application or some kind of the real world application. This is again the detailed side-by-side comparison of different approaches as compared to the cache hit rate. Uh, if you can compare these into the different methodology, our approach by using this exponential smoothing technique, because we are using this exponential smoothing, and this will help us to achieve the higher hit rate as compared to the other approaches. So overall, the approach increased the hit rate by 5.46 and reduced the query time by 6.34 as compared to the other state-of-the-art approaches. And this is again we applied on two different data set. So this is same. The hit rate is a direct result of our query augmentation and frequency based cache replacement policies, because we prefetches the similar queries and retaining the valuable data in the cache. That's why our overall cache hit rate is more as compared to the other state of the art approaches. Now, this is also interesting result on the hit rate and space overhead. So our approach is almost achieve 90% hit rate. As I told, this means that 9 out of 10 queries were answered from the cache, and this also reduced the server load and improved the response time. The space overhead is also less as compared to the other approaches like LRU and LFU, and also the time overhead. The time of overhead mean the hit checking time for the approach was just 280 millisecond, 10 times faster than the existing approach. So these results demonstrate the efficiency of our system. Also, we create a cache system that are fast and also resource efficient. This is particularly important for the application that require the real-time access of data, such as AI model or interactive data exploration tools. So to summarize our experimental result, our approach achieved 90% F-measure for maintenance quality, demonstrate high accuracy in keeping the cache up to date. We also executed fewer irrelevant updates and achieve a higher effectivity. So that as compared to the existing state of the art approaches, our system also deliver a hit rate of 90% and lower overhead, making it faster and more resource efficient as compared to the traditional method. So these results confirm that our approach is not only theoretically sound but also practically effective. So it addressed the core challenge of querying link open data and creating a system that is scalable, reliable, and efficient. Uh, if you have any question, you can also write to me. These are some of the selected references that I have put it over here. Thank you.